Okay, so yes, I was here, as Nicholas said, in 2023. I had a conflict in 2024, otherwise I would have come again, because I really enjoy this place and this event and the crowd I see at this event. And so I have been working on various projects on training large language models in Japan. And so today I'm going to introduce you to 3 separate projects that we have in Japan on training large language models. One is on training large language models on Fugaku. The one in the middle is a separate project. It's a consortium of many industry members, and it's led by NII, but it involves a lot of the big companies, like big national labs and academia. The one on the right is a completely separate effort that we are doing at our university. Oh, by the way, our university changed names from Tokyo Tech to Institute of Science Tokyo. So whenever you hear this university name, Institute of Science Tokyo, it's not some unknown, new university that, that has no credibility. It's formerly known as Tokyo Tech, Tokyo Institute of Technology, where I myself have been there for 10 years now. Satoshi Matsuoka was there for, I don't know, maybe 20 years. So yeah, it's the same university. We just changed names.
Short name.
That's a short.
There is no short name at the moment. Yeah.
It's like that.
Yeah, you could still call it TaiTech. Yeah, I actually prefer that.
I met you.
Yeah, the new TaiTech. Okay, so why are we doing this? Why is why are we training our own large language models? It takes like tens of thousands of GPUs and many months of them. Why are we wasting all this computational resource that could otherwise be used to do science on such things? So here's one way to justify this. So the closed models shown on this orange trajectory have been advancing very rapidly, but you see on benchmarks like MMLU, they are somewhat it also means that MMLU is no longer able to measure the capability of these models correctly. But on this particular benchmark, you see that the blue open models have pretty much caught up. I'm not sure what this last blue dot is. Maybe it's DeepSeek or something, but pretty much there has been this trend. It's not like DeepSeek suddenly came out and reproduced the thing that otherwise was unreachable. It was in reach, right? They were just barely the first ones to do it at that cost. So the cost has been decreasing, and the reproducibility of these experiments on the highest scores has been improving, right? We've been able to reproduce better and better models. And so because you can do it at much lower cost if you just wait for a few months, right? This new technology comes out that you can train faster, and the amount of parallelism increases, and then the training data improves, the training methodology improves. There's various ways to do reinforcement learning to get these reasoning models to work. So if you wait a little bit, the cost gets cheaper, exponentially actually. So that's why we're trying our best to approach this from different angles. One of the angles is using non-NVIDIA GPU architectures, and I know there's efforts to use AMD GPUs and Intel GPUs. This one is very extreme. Of course, this is a machine on in the top 10 of the top 500, but it's a purely CPU machine, and it uses ARM-based A64FX. So the first topic is what we did on Fugaku. So we managed to accelerate, like odd-sized and batched gem operations by 6x. We did very low-level optimizations in collaboration with Fujitsu, who is developing the libraries. And also, we accelerated the communication over the TOFU network by by accelerating the particular all-reduce algorithm that runs efficiently on the 6D torus network. And we use very low-level commands to do this. We got, in the end, like 3x speed up. So both communication and computation were accelerated. But in the end, like the peak performance of a single node on Fugaku is 6.8 teraflops. Now, compare that to, like a single B200 GPU, which has, like over a petaflop of performance, right? That's how disadvantaged we are if we try to use Fugaku. But one advantage is, they let us use a lot of nodes, right? So we used this amount of nodes for a few months, and this is about 1/10 of the machine, by the way. So it's not the full machine, and we achieved about 14 petaflops, which is equivalent to about 14 modern GPUs. But in the end, it scales better, so we could use way more nodes without any performance degradation. But the cautionary part of this particular story is the kind of problems you run into when you use a non-standard software stack for doing this kind of LLM training. So, of course, Megatron Deep Speed, because it relies on PyTorch on the back end, naturally runs on CPUs too, right? Like PyTorch runs on CPUs. So it runs on A64X CPUs off the bat, but to accelerate, you write these libraries, right? And some parts of these libraries are not as debugged and they haven't been used by many users, right? There's this sort of a fork of the Megatron Deep Speed that has been optimized for CPUs, and you have like things like one API or one DNN on the back end, and those backends have not been tested by too many users either, like compared to the NVIDIA software stack. And so you have all these bugs that you notice after like a week of training, right? If it would break in the initial parts, like here when you just start the training, then it makes our life a lot easier. But that doesn't happen. It starts misbehaving like way long into the training, and suddenly you get not a number, and this is caused by some custom hyperbolic tangent kernels. Like you need to go really deep into the software stack to really debug these things, and sometimes it consumes way more memory than it should. And these things, we've been using Megatron Deep Speed on the NVIDIA GPUs for a long time, or had been when we started this, and we got none of these errors, right? And so this is unique to the particular setting that when you use Fugaku to do it, you run into all these extra issues. I'm sure people doing it on AMD GPUs and Intel GPUs are facing similar problems, but to a lesser extent because they're at least GPUs. So the second effort is this huge consortium. Many university labs have joined. Mainly, it's a lot of NLP people, natural language processing people. The whole community in Japan, in particular, has been disrupted by LLMs. Basically, all the research topics that they've been doing became somewhat obsolete because of this capability of the LLM, especially in the natural language field. So they formed a consortium to actually be the ones who develop it rather than be cannibalized by the whole field transition. And a lot of industry joined. So that on the Slack for LLM JP, there's like 2,000 people in it, and like most of them are spectators. So they watch us, suffer. You see the Slack channel, and we're like exchanging messages about all these problems, and a lot of these guys are learning from it. That's fine, but yeah, it's supposed to be helping the whole industry in Japan by us completely doing this open. So we open all the data. Well, so this is open English corpus. Everyone can access this one. But some of these things, for example, the NDL, National Diet Library, gave us a lot of data, and we opened it. And so this is unique. Some of this is unique Japanese data that no one else had, but now we opened it. And we open all our configurations, the data, hyperparameters, all the settings. And so it's sort of similar to the Olamo kind of stance, where you open everything, data, checkpoints, and it's a Japanese version of that. We train on various machines with mostly NVIDIA GPUs. But so from here, I have like 2 or 3 horror stories again about. So we started training mid-size models, like starting from like 13 billion parameters. That's considered like mid-size language models, and then up to like 172 billion, which is considered quite large. And one issue that we ran into, I think this was like spring of 2023. So at the time, Llama 2 was the best performing open model, and we were reading the paper, and it says here, the epsilon hyperparameter should be 10 to the minus 5th, right? And so we did the experiments using that parameter for 13 billion, 70 billion, 172 billion, but something was wrong. Like the eval average scores weren't increasing. The loss was decreasing fine. So yeah, I'm not showing the loss here, but if you look at the training curve, everything is going nice. But when you actually run the benchmarks, it was performing horribly. And even we used the right value of the epsilon that we later found. And even for 13 billion, it performs much better than 70 or 172. So this thing, a lot of people I heard later ran into the same issue because they clearly write this in the paper. And it makes a huge difference. Now there's papers that explain why this should be decreased as the model size increases. But at the time, we didn't have such papers published. The next thing, so once we fixed that bug, we went from like 13 billion to all the way to 172 billion. And the second time we trained the 172 billion, these are all evaluation score averages. So this is the actual performance, not just the loss of this training. And you see the brown thing go up, and it sort of tapers off here. It's like stops increasing, right? And of course, this is a base model. So if you do like all the post training, then you get this instruction model, which is much higher. This black dot is GPT 3.5, and this yellow dot is GPT 4. So it's a little better than GPT 3.5, but GPT 3.5 has also around 170, I think it's 5 billion parameters. So it's a similar scale. So we somewhat reproduced that level, but at this point, GPT 4 was available to everyone. So yeah, we were aiming for this dotted line here. And then we went into the individual tasks. So the plot I was just showing is the average of many, many different benchmarks, right? That's how you benchmark these large language models. You don't just test it on one thing, you test it on everything, like fundamental analysis, mathematical reasoning, machine translation. I think this one's from English to Japanese translation, basic question and answering, and reading comprehension tasks. And there's many, many more. And then this is the average of 11, tasks that we chose to benchmark on. And you see, yeah, that this, there's this saturation of the performance on all of these benchmarks, but some of them you don't see it as much. It's just mildly coming to its upper limit. And here we also plot the GPT-4 scores. So wherever you see it approaching GPT-4, it's actually, that task is already too easy to see any significant benefit by improving your model anyway. So you should stop benchmarking on tasks like these, right? It's already saturated. You don't see any difference even if you get a better model. But tasks like this, there's still a huge gap between GPT-4 and us. So ones like these, so like math and analysis, these really require better models. And so an interesting way to map the train loss to your actual performance on each of these benchmarks. So interestingly, these plots behave, they have this S shape. So it looks like a sigmoid function, actually. And this means as your loss decreases, the x-axis is the loss, as it decreases, your score increases like this, right? So it starts out then at some point, at some train loss, it suddenly shoots up. And where it does this is different between all the tasks. But if you do this for all tasks and then take the average of these S-curves, then you can actually predict from the loss, so some hypothetical loss that you'll get in the future, you can predict the actual downstream performance. And it does a pretty good job doing this. And people who are developing huge models actually absolutely need to do this kind of a fitting study to not just measure the loss, because the scaling laws that people mention, that's all about the loss. That's about this x-axis here, right? It's promised to have low loss, but loss does not promise the downstream task performance, and there's a huge difference between the downstream tasks. So just looking at scaling laws doesn't get you the final performance that you need. And then something magical happened. So the 172 billion model that I was showing is this purple thing here. And then we started to investigate these mixture of experts models. So this 8 times 13b is a mixture of 8 experts. And I won't explain in too much detail about how mixture of expert models work in my talk. So if you want to know, you can talk to me later in the hall. But basically, this sort of saturation of the performance disappeared when we did this mixture of experts. Well, I don't think the change in the architecture is what caused this. It's some of the training settings that were changed that have nothing to do with the shape of the model. We use the exact same data to train all of these different colors, by the way. So the data is exactly the same, right? So this sort of shows you, depending on what kind of model you train, even on the same data, the exact same data, you get completely different performance. And this is why people are investing in a huge amount, right? This brown one is very expensive. Well, the purple one was the most expensive to train. The brown one is more efficient, and that's why we use these mixture of experts. But as you go up, the cost to train these things increases exponentially. But because you know that you're going to get this return, people are investing. Okay, so the last part of my talk is on this model called Swallow. It's named after the logo of our old logo. Tokyo Tech had a logo that has a swallow bird on it, and we named the model after that. Also, Tsubame, our supercomputer, means swallow, the bird, in Japanese. So it's sort of English of Tsubame. And then, so this one is trained in a slightly different way compared to the previous 2 ones. The one on Fugaku and the one LLM JP were trained from scratch, as they say. This one starts out from models like Llama 3 or Quen. these open models, because they open the weights, you can download the weights and continue the training from there. Whatever data they use to train up to there, we keep using that, the end result of that as a starting point, and then add some Japanese data, right? So the advantage is that it leverages all the training data that was used to train the original model, but it's unclear what the data was, what data the model was trained on, because no one besides a few selected groups actually opens the data, right? Many people open the model weights, but very few open the data. So for example, Llama 3, we don't know, we have no idea what kind of data they used, right? And so that's the disadvantage. And also models like Llama 3 400B or Qwen 272B, and more recently models like DeepSeek-V3 and R1 perform, they are very competitive in terms of the performance with the closed models. So why not just start from there, right? The weights are open. Okay, so if these models are open, then and they are trained on, at least some Japanese. So they speak pretty good Japanese, but the problem was not there, right? When we first started doing Swallow, this Japanese language model, through continual training, the problem was that this English sentence here, characters not in the vocabulary are broken down into UTF-8 bytes, consuming as many as 3 tokens per character. So what it says is correct. If you say the same thing in Japanese, right, it's like the worst case of what it's saying here. It's actually broken down. At most, you can actually see it. Some of these Chinese characters that we use in Japanese are broken down into like 3 tokens, right? Whereas, so each of these different colors, slices with different colors are different tokens. So English, this is 1 token. This whole purple thing is 1 token. This whole green thing is 1 token. In Japanese, all of these things are different tokens. And so if like OpenAI charges us per token, we're actually paying 3x as much compared to like English speakers. Basically, we're getting ripped off, right? And so this is a pretty strong motivation for Japanese people to retrain their models, like take some open source model like Llama, change the tokenizer so that it puts more Japanese in vocabulary into the tokens, and retrain the thing a little bit so that it doesn't forget the English, but it adds more. It sort of redoes the encoding part according to the new tokenizer. And to do that, we need Japanese data so that it learns these things again. And so we start from Common Crawl. So we are one of the few groups that actually redo the whole filtering process from the base Common Crawl data repositories. And we get pretty good performance. So the Qwen model is, this is a Chinese model, and its benchmark performance on Japanese understanding is better than any Japanese model, ironically. But the best one in Japan, so yeah, I admit, China is ahead of us, right? Okay, they have more resources, and they have more human resources, way more human resources. They have more GPUs as well. And so we're only a little bit behind, right, in terms of Japanese understanding. And we're at least the best within Japan. Our Swallow model that's based on Llama 3 is at least better than other models. We've also trained from things like Mixtral, and we call it Swallow MX. And there's a whole bunch of other models that are trained on Japanese, but there's like large difference in the capabilities. So it's not as simple as getting a huge allocation on AWS or Google Cloud and just running the best known model, right? You don't get the best performance by just doing that. There's a lot of work that needs to go into training large language models, and in Japan, we want to sort of, have the capability to build our own model, at least to some extent. Maybe not the best one, but at least try to catch up as much as we can. Okay, so coming back to what OpenAI is doing, they released O1 and then O3. And by the way, Grok 3 was released, I think, the day before yesterday or something. And they conveniently omitted the O3 performance from the chart they released. They didn't have these red bars, so someone added them correctly. And you can see that Grok 3 is not better than O3. And so, but that small difference doesn't really matter. That's not, these people are getting obsessed with these small differences, but that is not what is amazing here. It's this general trend that once these, reasoning models or, the test time compute models came out, they are advancing at a, insane pace, right? And I think this is going to continue for a little bit until like test time compute becomes too expensive, which it's offset by, a huge constant. So it's not going to become too expensive in the near term. So for the time being, math and coding and the stuff that Jeff mentioned to convert your code by using AI, this capability, these are coding benchmarks, code forces, SW bench. These are extremely difficult coding benchmarks, and they're scoring better than previous generations. Like GPT-4o is not even on this scale because it's like 10% or something, right? These are completely new capabilities in terms of coding and math. And so from a, the future perspective of these models are, we need to really change our mindset. It changes some few perspectives drastically, right? One, well, this is known, right? Benchmarks should have an expiration date. Look at all these benchmarks and they're all saturating. Like someone proposes impossible to solve benchmarks and like half a year later, it goes to like 90%, right? That's always, it's been constantly happening throughout the past decade that someone proposes a benchmark that's supposed to be impossible for, these models to solve. And, they even say, oh yeah, if you can solve this benchmark, you can claim to be AGI. And according to that, O3 is already AGI. So, we need to be careful because our models are basically only as good as our benchmarks, right? I showed this plot where it looked like the open models were catching up to the closed models, but we're basically just not able to measure that last performance increase, right? So if we stick to the old benchmarks, we're not going to know that the performance is getting better. We won't even notice. And soon, we won't be smart enough to generate difficult enough benchmarks. And that's where, we won't be able to understand if we achieved super intelligence or not because we're not intelligent enough to measure it, right? And I'm pretty sure that's going to happen soon. But in the meantime, scientists are the smartest people among the humans. And so AI for science is like the last place where humans are contributing to AI, right? This is going to be the last thing that happens, right? So this chart here is taken from the photon light source at Argonne. I sort of give this analogy now that, these things require a huge amount of electricity, right? You put in more energy, right? And then these supercomputers with like 200,000 GPUs are going to do AI for AI. So now that these things can reason and code, they're going to make themselves better and better automatically without us doing anything. And this is, as long as you pump in like gigawatts, this thing is going to keep accelerating and we won't even know how good it's getting. But science is one of these experimental halls that will take the enormous AI capabilities and channel it to our scientific domains. That's how I view AI for science. Not as something we build from scratch, but something that shoots off from these OpenAI, AI for AI accelerators. And when you look at it from that perspective, you really want to remove the restrictions in these models, right? So we went from classification to like segmentation and searching to generation, and now interaction. Every single one of these things really removes, the expressivity limits of these models, right? If you're just looking at a picture and thinking if it's a dog or cat, the capability or the knowledge inside this huge model is not really being expressed. Whereas if you're generating something from like thin air, generating a whole math equation or a theory or a paper, right? And also doing that interactively, the search space is huge and the expressivity space is huge too. And so that's where we're heading, right? Really, the ChatGPT breakthrough came from, changing this kind of classification mentality to a generation mentality, right? That's why these are decoder-only models. They're not like encoders. That was the old kind of, let's get the knowledge, express it in a concise manner, and extract things that are understandable. No, we just generate and let it do what it wants, right? That's much more better use of its capability. And also, this has to do a lot with AI for science, right? Is that particular science data that you want AI to do something with, do you really need to pre-train on it? Or do you want to fine-tune on it? Or do you want to do in-context learning on it? Or do you want to do something like deep research on it, right? By through, like retrieval. So this kind of view is like, the previous way to view this is for pre-training, data goes into the AI, right? We get huge data, domain-specific, we only have some data that's unique to us, and that's our advantage, right, in this mentality. And if we pump it into the AI, some magic happens and it outputs something we couldn't imagine before, right? But the new models, how they work, if you've played around with the latest deep research models, any of them, like from OpenAI, Google, or DeepSeek, they do things they think by themselves. The data that they use is external. It's not internal, right? They can go into the web, search things. You can give documents to them later on, not train on them, right? I think this is more like the AI agent going into the web. Or similarly, it could go into your scientific data, right? This is sort of the new way that these things behave, right? So I think it's really important. I think this is very domain-specific. For AI for science, each domain really needs to think, at which stage does your data need to be interacting with the AI model? Because the latter stages don't require any training. And as these models get better and better, more things are better dealt with on the later stages because it gives the model more freedom to retrieve and select. So yeah, that was my last slide. So yeah, the summary is we trained a lot of LLMs, and as a result, we sort of have a good idea of what DeepSeek, how it's good, and where we're headed is completely different from where we were, right? This whole new paradigm is completely different from the previous way of thinking. So yeah, I'm really optimistic, as you can tell from my tone. I really think that we ourselves can actually participate in this huge sort of advancement of both AI and science. And it's an interesting time. I'm very happy to be living in this particular time because amazing things are about to happen. So thank you.
Amazing.